Okay. So I think one student said he will take the seminar, but I forgot his name. Okay, so propeller is nothing but a rotating wing. So this also has the leading edge, then trailing edge, then root section, then tip section. This will also have some twist. Okay, and it is attached in the center hub. The only difference is it is a rotating wing. Okay, so this is also similar to the wing, but it is a rotating wing. And this is the front view, this is the top view, this is the constructional view. Okay, and you can see this cut section, the thickness is more near the root section than near the hub, then it is keep on decreasing and become thin at the end. You know why it should be thick in the hub section to withstand the bending moment, etc. and all. And if you see this angle of attack, it is decreasing. What is the reason? Any idea? Can you say whether it is wash in or wash out? You studied, right? Wash in, wash out. So root section, the angle is more. Tip section, the angle is less. Then what is the configuration? Wash in or wash out? Hello? So this is like a washout, right? So am I audible? No one is responding. So hello?
Yes, sir.
Yes, sir, you're audible.
Okay. So towards the root section, the incident angle is decreasing. The reason is, you know, the velocity, it will increase with the increase in radius. Okay, always the tip speed will be more, right? Okay, the velocity is less near the root section and it is keep on increasing towards the tip section. So the velocity profile may be like this. Okay, so as the velocity is maximum in the tip, here also if you keep the same angle of attack, more angle, okay, so the flow will be accelerated to the maximum condition. So it may achieve some critical Mach number, that is there may be a shock wave. Okay, also you will get the uneven lift distribution. Here more angle, here the more velocity. Okay, more angle, more velocity, here more angle, less velocity. So you will get uneven lift distribution. So to avoid that shock wave formation, also to maintain the uniform lift distribution along the radial direction, we are decreasing the angle of attack, incident angle. Okay, so that we can maintain the uniform distribution. Also we can avoid the shock wave formation in the tip. Is that clear? So towards the tip, angle is less, so that we can avoid the shock wave formation. Also we can get the uniform lift distribution. Okay, if you keep the same angle everywhere, then the lift distribution will be like this. It is not even, then there will be more bending moment, stress, etc. and all in the hub. So this is the structure of the propeller. And so this portion is shank. Okay, it is like a bluff body. So normally what they will do, they will cover this with a cuff, some rubber structure they will give it to convert this, what is it, bluff body into the streamline body. I think I have it, the last slide, like this. Actually it will be like this, like a cylindrical portion. So instead over that they are giving some rubber boot, okay, with a streamline shape, so that they are reducing the drag produced by this shank. You can see this additionally attached here also. If you remove this, it will be like a cylindrical portion. Is that clear? This cuff. So in the one word they may ask, what is the use of cuff? It is to reduce the drag produced by this shank. So this is the shank, okay, SKShank. So this is the structure, and these things also they will ask in 1 mark, 2 mark. So geometric pitch, effective pitch, and slip. So first I will explain the geometric pitch. So geometric pitch means the distance the propeller should advance in one revolution. Okay, you know the propeller is rotating, also moving forward, right? I have one video also, so let's play it. Alright. Okay, it was here. So, okay. So propeller is rotating, also it is moving forward, right? So in one revolution, how much distance it forwards, advances, is the geometric pitch. Okay, so this is the ideal case. In one revolution, the distance it should advance is the geometric pitch, but in real condition, there will be a viscosity, there will be a compressibility effect. Due to that, there will be some loss. Okay, so ideally, it has to move up to this distance, but in the real condition, there will be a viscous effect, etc. and all. So there will be a loss. So what will happen? We will get only this effective pitch. Only this much we could move in the real condition. So the definition of the effective pitch is the propeller, there is the distance the propeller advances in real condition with the slip. Okay, so this is without slip, the distance the propeller advances without slip. This one is the distance the propeller advances in one revolution with the slip. The slip is the loss, distance difference between geometrical pitch and effective pitch. Is that clear? So they may ask like the distance the propeller advances in one revolution without slip means it is geometric pitch. If they mention with the slip, then it is effective pitch. Is that clear? The loss is slip. Is that clear?
Yes, sir.
Okay. And as I mentioned, propeller is rotating, also it is moving forward. So mostly we will take the relative speed only. So the propeller has axial component, also the tangential component. Okay. So if you take the cut section in the propeller, we can see the aerofoil cross section like this. Okay, assume the blade is like this. If you cut, you can see this aerofoil profile. As I mentioned, there is the axial velocity, also the tangential velocity. So this is the axial velocity, relative axial velocity. This is the relative angular velocity or tangential velocity. Due to that, we are getting the relative wind to this aerofoil. Okay, we have two components. Due to these two components, we are getting the resultant velocity in this direction. That forms the angle of attack with respect to the chord line. Due to this angle of attack, we are getting the positive force, resultant force. So it is almost similar to the wing. Okay, so axial velocity, so angular velocity, due to that we are getting the resultant velocity that forms the positive angle of attack. So we are getting the resultant force. Resultant force will be inclined rearward. So normally in the wing we are resolving the resultant force into lift and drag. Okay, so lift will be perpendicular to the free stream velocity, that is relative wind. Drag will be parallel to the relative wind. So we used to really what is it? So derive lift and drag from the resultant force, or we will resolve this into normal force and axial force in the wing. But in the propeller, instead of normal force and axial force, we are resolving that into thrust and torque force with respect to the plane of rotation. Okay, this normal force, axial force, it is resolved with respect to this chord line, right? So here also, if you want, you can resolve these forces. You can find normal force, axial force with respect to chord, but we are not interested in this normal force, axial force. So in the propeller, we are interested in the thrust. So we are resolving this R into thrust and torque force. So it is resolved with respect to this plane of rotation. Okay, so lift and drag is with respect to the relative wind. Okay, normal force and axial forces with respect to the chord line. Thrust and torque forces with respect to the plane of rotation. Okay, this is the difference. And this torque force means, so force is equal to, that is torque is equal to force into the radius. Okay, so instead of this force they are writing in terms of torque, because torque we can easily find it from the rotation. So instead of F they are writing dq by r, torque force. So at last we will find what is the thrust, what is the efficiency, etc. and all. Is that clear? Forces acting on the propeller. So here also there will be a certain force that we are resolving into lift and drag or thrust and torque force. And another thing, so this is the axial, this is the angular, because of that we are getting the relative wind that forms the positive angle, so we are getting lift, drag, etc. and all. So you know, so upper surface we have the low pressure, lower surface we have high pressure. This also they are asking 1 mark. Okay, how the static pressure varies along the propeller. So they may ask, so the static pressure in front of the propeller is higher than the lower surface or behind the propeller or free stream, something and all they will ask. So always in front of the propeller static pressure is low, behind the propeller static pressure is high. Due to the pressure difference only we are getting the resultant force, lift, thrust, etc. and all. Don't forget. This will be on 1 mark. Actually you can explore for the wind turbine. I used to explain that also. Maybe in my notes you can find it. Wind turbine, it behaves in the opposite manner. So wind turbine means pressure distribution will be, everything will be reversed. I think I don't have the content here. I will explain in the next class how the pressure distribution, velocity, everything varies for the wind turbine. It is not in the syllabus. Additionally, I used to explain. Okay, so propeller means in front low pressure, behind that high pressure. This is one mark. And these are all the other forces acting on the propeller. So first one is centrifugal force. Okay, this is a centrifugal force. So due to the rotation, so there is a force which tries to pull the blade out of the hub in that perpendicular direction. So this is called centrifugal force. Okay, this you know, right? In the school days itself you are studying centrifugal force. Okay, so due to the rotation there is a force which tends to pull the blade apart from the hub, that is called centrifugal force. Then torque bending force. So this green color shows the rotation of the propeller. Okay, anti-clockwise direction the propeller is rotating. So if it is the ideal condition, that is there is no viscous, that is inviscid fluid, means there is no air resistance, so the propeller will freely move. Okay, but in the real condition we have the air with a viscous property. Viscous means air resistance. So due to the air resistance, okay, the blade will be what is it, bent in the opposite direction little bit. Okay, so the blade has to rotate against that air resistance, so there will be a small bending force in the opposite direction, that is called torque bending. Is it clear? So due to the air resistance there is a small bending in the opposite direction of the rotation on the propeller, that is called torque bending. The next one is thrust bending. You know the purpose of the propeller is to produce the thrust, so that thrust bends the propeller in the same thrust direction, that is called thrust bending force. Is that clear? No one is responding, I am simply going on. Yes, due to the, okay, so due to the thrust the blades are bending in the forward direction, that is thrust bending. Then aerodynamic twisting force. So you know mostly the forces we will place it in the quarter cut point. Okay, so assume here the force is acting, but the propeller is attached in the center point. Now what will happen? This force will create some moment about this center point. Due to that there will be an increase in angle of attack. Okay, the blade try to change to the higher angle. That type of twisting force is called aerodynamic twisting force. So the blade is attached in the center point, but we know the force will be acting near the quarter cut point, so that creates some additional moment. That moment is try to increase the angle of attack of the blade, so that is called aerodynamic twisting force. Is it clear? So next one is centrifugal twisting force. Here what happens? So this is the flow direction. That flow hits the bottom surface. So that what happened? This flow tried to bring the airfoil in the normal, that is aligned with the airflow condition like that. Previously it is like this. Okay, the airflow hitting their bottom surface and trying to bring the aircraft to the horizontal position. Okay, this type of twisting force is called centrifugal twisting force. So here the flow trying to reduce the angle of attack. Okay, it is applying the twist so that the angle of attack is trying to reduce. So the difference you can see, the aerodynamic twist means it tries to increase the angle of attack of the propeller, but in the centrifugal twisting means it tried to reduce the angle of attack of the propeller. In the one word they will ask, so which force try to reduce the what is that, pitching angle of the propeller. Okay, if the angle is try to reduce, then it is centrifugal twisting. If the angle is try to increase, then it is aerodynamic twisting. These things and all they will ask in 1 mark. Is that clear?
Yes, sir.
Okay, so these are all that 5 forces we discussed: centrifugal, torque bending due to the air resistance, then thrust bending due to the thrust, aerodynamic twisting force, so due to the moment created by the force. So here the angle is try to increase, here the angle is try to reduce, centrifugal twisting force. Then types of propeller. So the first basic type is fixed pitch. You can see, so it is the single piece propeller. Okay, it may be made up of wood or aluminum alloy. So single piece means you cannot change the blade profile or blade pitch angle, etc. and all. Okay, it is fixed. Mostly this type of propellers were used in the smaller aircraft, in very old smaller aircraft, maybe smaller propeller aircrafts. So this mostly used for low range, low altitude, low speed aircraft. Okay, so we cannot change the profile. This is first type, fixed type. Is that clear? Fixed pitch, a single piece propeller. All the geometries are fixed, made up of aluminum or wood, mainly used for the low speed, low range, low altitude aircraft. This is fixed pitch. Then further they improved this design to the ground adjustable propeller. So this also made up of aluminum or wood. Now you can see this is two pieces. This is one piece, this is one piece. Two pieces joined in the hub. The what is it? What is advancement means? Before starting the aircraft, we can adjust the pitch angle, depends upon the mission, whether it is very short range mission or whether it is a short range mission or medium range mission. Depends upon that, they will fix the pitching angle, then they will start the aircraft. Okay, so the pitch angle cannot be adjusted during the flight. Before starting the flight, we have to adjust the pitch angle, depends upon the mission. Is that clear? Ground adjustable.
Yes, sir.
Okay, then further they improved this design to the controllable pitch propeller. Okay, so here also two piece attached in the center hub, but the advantage is, so this one we cannot change during the flight. Before starting the flight we have to adjust it, but this one we can adjust during the flight also, but to the two angles. One is minimum angle, that is fine pitch angle. Another one is maximum angle, that is coarse pitch. Okay, so only two angles we can change. So during the flight itself, the pilot can change the pitch angle to the minimum and maximum, fine pitch and coarse pitch. You may ask, what is the purpose of this fine pitch, coarse pitch? So I will tell you. I think I have some video. You can see just starting, and from the thickness you can find what would be the pitch angle. It is less. Okay, the thickness is less actually here during the takeoff. that means it is fine pitch, minimum angle. Now once the speed increases, see it is less, okay, the thickness. Once it is in the, as the speed increases, you can see this angle also increasing. You can see. So previously it is very small, now it is increased to the maximum, right? I'll explain why they are changing, etc. and all. Let's see this video also. Have seen this video? Should I repeat it? Replay the first video. You can see it is in the cruise stage, so the pitch angle is more. You can see the thick blade profile here, right? And now it is reducing and it is about to land. You can see how much the angle is reduced. It is very thin, that means very low angle. Okay, as the speed reduces, angle also reduced. This is clear, right? How the angle changed. Should I replay? So very low angle. Then at the cruise, the angle is increased. The reason is during takeoff and climb, velocity is less, right? The forward velocity is less, but during the cruise, the forward velocity is very high. Okay, this you know that already. Now we will come to the blade profile. Assume this is during takeoff. Okay, so the propeller is rotating, also moving forward. This forward velocity is less during the takeoff. So assume this is the forward velocity and this is the rotational velocity. Due to that, I am getting the resultant velocity. Okay, that resultant velocity forms the positive angle of attack. So I am getting resultant force. Then we can resolve into lift, drag, etc. and all. Okay, this is the first case. Now the same aircraft, it reaches the cruising speed, maximum velocity. That means forward velocity is increased. Okay, if the forward velocity is increased, now we have to find the relative wind that goes like this. Okay, same propeller. Now the forward velocity is increased in the cruising stage. Because of that, this component is increased. Now if you find the angle of attack, so this is the chord line, this is the relative wind, we are getting some negative angle. Okay, so if you don't change this angle, what will happen? We will get some negative lift, or it won't produce the lift at all. So in that case, this airfoil angle should be increased. Okay, from minimum to maximum we have to increase it. Is that clear? As the forward speed increases, angle of attack also the angle of attack also has to be increased, then only we will get the positive lift, otherwise it will produce only the negative lift. Is that clear, or should I explain again? Okay, rotational speed, axial speed, because of that we are getting the relative wind direction, so it is positive angle. Okay, for the same wing, if the forward velocity is increased, now you will get the negative angle, that means negative lift. So to avoid that, we have to increase the blade angle further higher, so that still we can maintain the positive lift and positive angle of attack and positive lift. Is that clear? What is the need of coarse pitch and fine pitch? I tell something, or shall I repeat, or hello?
Yes, sir.
Okay. So here only one angle, before starting we can change it. Then controllable pitch, third one pilot can change the angle to minimum and maximum, fine pitch or coarse pitch. So during the takeoff, he will maintain the fine pitch. Then during the course, during the cruise, he will maintain the coarse pitch. Okay, when the velocity is high, the angle of attack also will be high. Like that, he will change it, depends upon the operation. Then further they advanced the design, that is constant speed propellers. So here what will happen? We will have the speed governor instrument. Okay, that speed governor will adjust the pitch angle depends upon the velocity. Okay, so even in the previous controllable pitch propeller, we are changing only two angles. One is for this takeoff and climb, even though the velocity is not constant throughout this profile, we are maintaining one angle here and another angle here. But if you want full efficiency, then the angle has to be changed for every change in velocity. Okay, from here to here, everywhere the velocity is changing. So that is done by this constant speed propellers. So we have the speed governor instrument that will sense the speed. Based on that, they will adjust the pitch angle throughout the mission. So we are getting full efficiency. This is the advanced one. Nowadays, everywhere we are using this constant speed propeller with the help of speed governor instrument. It changes the pitch angle for change in velocity. Is it clear? The next one is feathering propellers. Any idea? You might have come through these steps and all, right? Many students I hear they are interested in the propellers, quadcopters, etc. and all. Anybody in the SCRO team or UAV team something?
Yes, sir.
Then you should
Yes,
work
sir.
with this propeller, etc. and all, right? Okay, at least it's good. You join somewhere in other extracurricular activities. So next one is feathering propeller. So here what happens? Assume we have two engines. Okay, mostly this feathering propeller we will use it in the one engine operating condition. That means one engine is failed, only one engine is operating. In that type of conditions, we will use this feathering propeller. So normally, if the propeller rotates, this is the angle, this is the thickness we have to the flow direction. Okay, but if it is not rotating, then unnecessarily the profile will produce some drag. Okay, if it is rotating, it is totally different. It is not rotating, and if it is like a thick structure, this thick structures will create unnecessarily more drag. To avoid that, they are changing this blade in such a way it is aligned to the flow direction. That is called feathering propeller. Okay, so normally this is how the blade will be. Okay, when it is rotating, but in the one engine operating condition, that means assume this engine is failed. If you don't change the angle, it will be like a thick profile that will unnecessarily create the more drag. So they are changing the pitch angle so that the blade is aligned to the flow direction. This is called feathering propeller. So here further they explained. This is how the blade angle will be fixed, 20 degree, 30 degree, etc. When it is rotating, it is not an issue. But if it is not rotating, this is the flow direction, axial flow direction. You can see this creates this much drag if it is not rotating. Okay, only if it is rotating, then the flow will be like this. If it is not rotating, it is like a flat plate kept in the airflow. It will create more drag. In that case, we have to change the angle to the 90 degree so that it is aligned to the flow direction, so that we can reduce the drag produced by this non-rotating propeller. Okay, this effect is called windmilling effect. So is that clear? Feathering propeller, where we will use it, how we are changing the angle and reducing the drag. Is that clear?
Yes, sir.
Okay. Then reverse pitch propeller. So normally we will have a positive angle, but we can change the angle to the negative also. Negative means then it will produce the negative thrust. Okay, this is the forward direction. But if you change it to the negative angle, it will produce a negative thrust. The main purpose is like a aerodynamic braking. Okay, to reduce the speed, we can go for this reverse pitch with a negative thrust, so that we can do the aerodynamic braking. But the aerodynamic braking you should do only after the landing. only during the ground run. Okay, you should not reverse the pitch angle during the flight. If you reverse, blade will be broken. Okay, so you should not using this reverse pitch during the flight condition. Only after the landing, during the ground run, just to reduce the landing distance. Okay, the flight is landing like that. After the ground run, you can use this reverse pitch to reduce the landing distance. So reverse pitch propellers are used for the aerodynamic braking purpose. Is that clear?
Yes, sir.
Okay. Then another arrangement of propellers before that. So in front of the propeller, the flow is uniform, that is only horizontal. But due to the rotation of the propeller, this flow will have some tangential condition. Now it is only axial. Okay, due to the rotation, then the flow will have some tangential component also. So the slipstream means that is flow behind the propeller. It will be spiral. Okay, so before the propeller it is axial, but due to the rotation, the tangential components also included in the flow component. So the flow will be spiral behind the propeller. So flow behind the propeller is called slipstream. So because of that spiral slipstream, sometimes it hits the vertical rudder, vertical tail. So because of that, what will happen? There will be a yaw moment. Okay, so it is hitting like this, so that there is a yaw moment in the maybe anti-clockwise direction. This will happen due to the spiral moment. So to avoid that, what we have to do? We have to move the rudder to the same direction. Now the rudder is like this. We have to move the rudder in this direction. Okay, like this, so that we can induce the clockwise movement. Okay, so this slipstream produces anti-clockwise movement, yaw condition, and if you turn the rudder in the same direction, so this will create the clockwise movement, so that it will get balanced, so we can go in the forward direction. Otherwise it will be in the right side if you don't apply this rudder. This is the difficulty we are facing because of the single propeller aircraft. Is that clear? So the slipstream is spiral that hit the vertical trail and makes the aircraft to yaw in the, for example, left hand side. So in that case, you have to adjust the rudder to the same direction, so that we can get the anti-clockwise movement, so that we can maintain the aircraft in the steady level condition, in the what is that, forward condition, straight forward condition. So this is the issue we are facing with a single propeller. So to avoid that, they change the arrangement of the propeller. So here they are using the counter rotating propeller. So this propeller is rotating in the clockwise direction, anti-clockwise direction. This propeller will rotate in the clockwise direction, so that both the spiral effect will get cancelled, moment will get cancelled. Is that clear? This is called counter rotating propellers. Two propellers rotating in the opposite direction, so the moment will get cancelled. Then another one type is contra rotating propellers. So here we have two propellers in the same shaft, but one is rotating in the clockwise direction, another is rotating in the anti-clockwise direction. Okay, this is contra rotating, again to balance the moment, unbalanced moment. Then this one is just further modified. So contra rotating, also counter rotating propeller. So these two propellers are contra rotating, same axis, both are rotating in the different direction. And if you compare this set with this set, both will be in the opposite direction, counter rotating. Okay, combination of contra and counter rotating, like that different combinations are there. So this is for the arrangement, counter, contra, combination of both. Then arrangement of propeller and the fuselage. We have two types, pusher and tractor. So in the tractor means propeller will be in the front, and this propeller will pull the aircraft in the forward direction. Okay, here this propeller pull the aircraft in the forward direction. So this is tractor type. In some aircraft you can see the propeller in the behind the fuselage. So this propeller pushes the aircraft in the forward direction. So this is pusher configuration. Is that clear? Tractor and pusher.
Yes, sir.
Okay, so almost all the conventional aircrafts are the tractor configuration, which pulls the aircraft in the forward direction. But if you see the UAVs or the seaplane etc. and all, pusher configuration, blade will be in the big end that pushes the aircraft in the forward direction, and this is combination of both tractor and pusher, both are attached. Okay, that type of also available, push-pull configuration. Fraud momentum theory. So here we are going to find thrust and efficiency. So this is the control volume we are going to take it. So you know in the free stream velocity. Okay. So the free stream velocity will be less. Then what happened? The propeller adds the momentum, that is sucks the free stream flow and pushes to the very high velocity, right? So velocity will be less and it will be increased in this direction. Okay, the rotating propeller is sucking the free stream flow and pushes to the very high velocity rearward. Okay, so the velocity is increasing in this direction, that's why the area is decreased. So we used to assume the density is constant. Okay, so this subsonic flow, so mass flow rate should be constant, rho a v. So as it is constant, now we are considering only the a and v. Okay, if velocity is increases, so area is decreasing, that's why we are getting this type of control volume. The control volume is decreasing in the flow direction. Is that clear? So the flow pushes the propeller pushes the flow rearward with very high velocity, so area is decreasing. This is basic only. And in the front it has only the axial component, but due to the rotation of the propeller, the tangential component also included, so we are getting this type of spiral flow. Okay, 1 minute. Is it? Oh, yes. Okay. Sorry for the delay. And actually here we should place our propeller, but in this derivation they are assuming instead of propeller they are assuming one small circular disc. The disc is called actuator disc. Okay, so instead of the propeller they are considering one thin disc that is called actuator disc, and the actuator disc shows the same flow behavior as the propeller. So in the front it is low pressure, behind that there is a high pressure, so the pressure changes discontinuously. Due to that it is producing the thrust. Okay, so instead of the propeller we are replacing that with the actuator disc. It behaves with the same manner as the propeller. Is it clear? These are all the assumption we have. Here only axial, here it is spiral, area is decreasing, velocity is increasing, and instead of propeller we have actuator disc. So that, and this also already we discussed. Axial flow, tangential flow, we are getting resultant flow in this direction, so positive angle, we are getting resultant force, lift, thrust, etc. and all. Above the aerofoil low pressure, behind the aerofoil it is high pressure. This also we discussed. So using these two, now we can draw the final control volume, 2D control volume, also how pressure and velocity varies. So initially the flow is free stream. Okay, some free stream velocity v1 and pressure is p infinity. That flow is sucked by the propeller and pushes rearward. At last again that will reaches the free stream condition. So free stream pressure and behind also I have taken, but velocity will be higher. Okay, and propeller only rotates and produces the pressure difference in front and behind it. Due to that we are getting the propeller velocity v. Okay, so this is the propeller. So in here you have taken hello, am I audible?
Yes, sir. Yes, sir. Yes, sir.
Okay. Okay. Due to some call, my meet is disconnected. Sorry. Okay. So if you draw the pressure distribution, initially it is free stream flow. In front of the propeller, the pressure will be less. Behind the propeller, the pressure will be more. So free stream is decreased to the minimum pressure in front of the propeller, and behind that suddenly it is increased. Discontinuous. There is no continuous changes. Okay. Here low pressure, here high pressure. There is no continuous flow here. Then that high pressure again decreased to the free stream condition. Okay. Like this we are considering. This is the propeller. Like that we are taking the free stream, here on free stream, here on free stream, and blade. These conditions we are taking. So in front also you see the pressure difference, high pressure to low pressure, the velocity is increasing. Behind the propeller also high pressure to low pressure, so it is further increasing. So that's how pressure and velocity changes across the propeller. Is that clear? So due to this pressure difference, it produces the thrust in this direction. Now this is our final control volume. Free stream pressure, free stream velocity, slipstream pressure, both are same only. Slipstream velocity and propeller blade velocity is V, and in front we have low pressure, behind that we have high pressure. So I am taking free stream area is A1, blade area is A, and slipstream area is A2. We can find the mass flow rate also. So in the station 1, if you find it is rho A1 V1. Here if you find it is rho A and V. Here if you find it is rho A2 and V2. Like that we can find the mass flow rate everywhere. All those things are constant. So this is the control volume. Density is constant. Is that clear, this control volume? So velocity is increasing, so area is decreasing. So now our aim is to find the thrust force and efficiency. So here you can see, we can, for example, if the aircraft is flying in the sea level condition, we know what is the sea level free stream static pressure. Even we can find at what speed it is flying. Okay, these things are known. Then which is known as the blade area. The blade area will be known. Only these three parameters are known. P1, P2, blade velocity, slipstream velocity, this area, etc. are all unknown. Okay, so finally we have to write this thrust and efficiency in terms of known parameters. Only this P or V1. Okay, that is the idea here. So to write the thrust equation, I am taking Newton's second law. F is equal to m dot dv. M dot is mass flow rate. So I can take mass flow rate at any station, but I am going to take it in the blade section because I know the area here. Yeah. So I know density and area. So I am taking mass flow rate at the blade section, rho AV. You can take it anywhere, not an issue. So instead of m dot, I am taking rho AV, and del V, the velocity difference, slipstream and the free stream. Due to the velocity difference only, we are getting the thrust. So we can write thrust like this in terms of velocity. Okay, one form. Or here also all are unknown. We don't know the blade velocity, we don't know the slipstream velocity, unknowns are more. So I am writing another one thrust equation in terms of pressure. This is in terms of velocity, here it is in terms of pressure. You know, simply it is pressure into area. Force means here it is pressure difference into area. So due to this pressure difference on this propeller, we have the thrust. Okay, so the thrust formula will be P2 minus P1 into A. Okay, pressure into area, high pressure to low pressure, and area. So I can write thrust in terms of velocity and pressure. Is that clear? These two equations. M dot dv, A dp. Thrust in terms of velocity, thrust in terms of pressure. Here also P1, P2 are unknown. Okay, so unknowns are more. So I am going to equate these two thrust equation. Okay, this is in terms of velocity, this is in terms of pressure. If you equate, finally you will get this. Here also again unknowns are more. So further, if I want to simplify, I have to write this pressure in terms of velocity. Then somehow I can cancel the velocity and simplify. Okay. So I got two thrust equations. One is in terms of velocity and pressure. Equate. Unknowns are more. So if I can write this pressure terms in terms of velocity, I can cancel few velocity term to simplify. So to convert this pressure into velocity, I am taking the Bernoulli's equation because we assume density is constant, incompressible. I can take Bernoulli's P plus half rho V square is equal to constant. Okay, so I am going to apply that Bernoulli's equation in the station 1 and in front of the propeller, between these two stations, then behind the station behind the propeller and the slipstream. Okay, so A and B, then between C and D. We cannot apply between the propeller because the pressure changes discontinuously. Here and all the changes are continuously changing pressure. Here there is a blade, in front we have low pressure, behind that we have high pressure. Pressure change discontinuously, so we cannot apply the Bernoulli's in this region. I can apply only here and here. Okay, now let's apply the Bernoulli's. So in the station 1, if we apply P plus half rho V square, okay, P plus half rho V square, and in this station P1 plus half rho V square, velocity is same, blade velocity. Then between C and D, if we apply P2 plus half rho V square, then D, P infinity plus half rho V2 square. Like that I got two Bernoulli's equation. Then 6, this minus this will give you P2 minus P1 in terms of velocity. Okay, so just to convert this P2 minus P1 in terms of velocity, I use this Bernoulli's equation, apply it in front of the propeller and behind the propeller. Okay, not across the propeller because it changes discontinuously here. So from that I got this term P2 minus P1. So this is what we derived just now, P2 minus P1. Now we can substitute the term here. Okay, we will get this, then rearrange and cancel. Finally we will get blade velocity V is equal to V1 plus V2 by 2. Okay, so instead of P2 by P1, substitute this term, then rearrange and simplify. We will get blade velocity is equal to free stream velocity plus slipstream velocity by 2. That is the average velocity of free stream slipstream gives the blade velocity. This is the first equation we are finding. But here also the V2 is unknown. V1 is known, free stream velocity, V2 is unknown. So further I am going to modify this. For that I am introducing the term axial flow factor A. The definition is del V by V1. That is, for the given free stream velocity, what would be the incremental velocity the propeller can produce? Okay, for the given free stream velocity, what would be the incremental velocity? How much velocity the propeller can increase? That is the axial flow factor, del V by V1. Okay, this is also a given parameter. If you are buying the propeller, so they will give what are the airfoil they use, what is the pitch angle, what is the A value, everything they will give. Okay, so these are all the given value, axial flow factor. So now I can write this blade velocity in different way. So I can write it as V1 plus del V, that is free stream flow plus incremental velocity. That from that I can find the blade velocity. So I am rewriting this blade velocity using this axial flow factor, that is free stream velocity plus the incremental velocity. I will get the blade velocity. This is the equation I am getting. From this, if I take V1 outside, you will get this, and del V by V1 is A. This is the final blade velocity. So we know the free stream velocity V1, we know this axial flow factor, it is also given design parameters. From this we can find what would be the blade velocity. Is that clear? So all are known parameters. Now I can go for the slipstream velocity. Okay, because we don't know V and V2, right? Only V1 we know. Now we can go for the V2. So So this relation just now we found it in the previous slide, V1 plus V2 by 2. So instead of V, you can substitute this and rearrange. You will get V2 is equal to V1 plus V1 into 1 plus 2A. So this is also everything known parameters, free stream velocity and axial flow factor. Now we have written blade velocity, slipstream velocity in terms of known parameters. Then we can go for the thrust equation. This is the thrust equation, we got it. M dot dV, that is rho AV, V2 minus V1. Now we can substitute this V and V2 here. Okay, substitute V and V2. Finally, you will get this thrust equation. Okay, 2 axial flow factor given. We know the depends upon the altitude, what is the density. We know what is the propeller blade area. We know free stream velocity. A also given. So all are known parameters. From there we can find the thrust. Is that clear? Hello? Should I repeat any steps? So this is the control volume we have taken. Across the blade we have pressure difference, low pressure, high pressure. Okay, here free stream conditions. This is free stream, this is slip stream. Velocity is increasing throughout the control volume V1, V2. So mass velocity is constant. First I am finding thrust using Newton's second law, m dot dV. This is m dot, this is dV. Then in terms of pressure, okay, the thrust is due to the difference in pressure, P2 minus P1 into area. So equate, then convert P2 by P1 in terms of velocity using Bernoulli's. Apply in front of the propeller and behind the propeller. Okay. Then 6 minus 5 will give you P2 minus P1 in terms of velocity. That you substitute here. Now we got one equation. It tells blade velocity is the average velocity of free stream and slip stream. But again unknown is there. So I am introducing the axial flow factor. For the given free stream velocity, how much velocity the propeller can increase? What would be the incremental velocity the propeller can give? Will be by V1. From that I am getting these two velocities, V and V2. Substitute here. From that I am getting this final thrust equation. So this is one finding. The next one is propulsive efficiency. So it's simply power output by power input. So power output is the thrust produced by the propeller and the free stream velocity. Okay, thrust into velocity. This is the power output. What will be the thrust produced by the propeller? Then power input will be the change in kinetic energy to the air. Okay, due to the rotation, the momentum is RR to the air, right? So the change in kinetic energy is the power input. So due to the change in kinetic energy, we are getting this thrust. So of m dot v square. So it is velocity difference. So this is power output. This is power input. Now instead of thrust, I can write m dot v2 minus v1. Simplify. So different steps are there. We can write it in any form. Okay. So this is one form we will use it. 2 divided by 1 plus v2 by v1. Or this I can write it as, that is 2, if you take it to the denominator, it will be v1 plus v2 by 2. That is equal to v. So this is the another form, propulsive efficiency, v1 by v. Or instead of v, I can write v1 into 1 plus a. If you get cancelled, you will get 1 divided by 1 plus a. Like that we can write the propulsive efficiency in different form. Okay, so power output by power input, thrust into velocity, free stream velocity divided by change in kinetic energy of m dot v2 square minus v1 square. Substitute thrust, simplify. We can write that propulsive efficiency in different forms. Okay. So this they may ask in 1 mark. What is the propulsive efficiency? The answer is a, like that they will change it. And in the 1 mark they will ask Okay, is that clear? Propulsive efficiency. So we discussed thrust, then propulsive efficiency in different form. Now we will see how the propulsive efficiency varies for different aircraft. So here I have taken set of engines, propeller, turboprop, turbofan. You know this is very low speed. This is used in the very small aircraft. This is turboprop. It is used for some medium type of aircraft. Velocity is little bit high compared to that. And turbofan, low speed commercial aircraft. Okay, passenger aircraft, little bit higher. But overall, if you see the velocity, it is less only. Okay, all are very low subsonic speed only. Okay, so these engines produces very less velocity difference across the engines. So this is the engine fan. It produces very less velocity difference. If the velocity difference is less, then this ratio also less, then the efficiency is increasing. Okay, this time is decreases means this will increase. So propeller, turboprop, turbofan, everything produces the higher propulsive efficiency, but definitely compared to this will produce more efficiency. Compared to this will have the more propulsive efficiency. Okay, sometimes they will ask the order. So this is the first place. This produces very high propulsive efficiency, and this is second. This is third. Finally, we have turbojet. Turbojet, you know, right? What is it? Used for the high-speed operation in the military jet, etc. And all you can find these small turbojets only. I think I heard this Blackbird aircraft. I think yes, 17 or something Blackbird aircraft. You can see a turbojet engine with afterburner. It can fly up to Mach number 3.5. Okay, so these type of turbojets are used for the even supersonic speed. That means this produces very high velocity difference. Okay, so these are all used for the subsonic turbofan, up to turbofan used for subsonic. So velocity difference is less, so efficiency is very high. But these turbojets, it is used for supersonic speed, so the velocity difference will be very high. If this ratio increases, then efficiency will decrease. Okay, so after the turbofan, we have the turbojet. Okay, this is the decreasing order. So best efficiency is propeller, then turboprop, then turbofan. After that, we have turbojet. Okay, so propulsive efficiency is increasing in this order.